Okay. Well, thank you everyone for being here. My name is Adam Rumpf. I'm an instructor at Florida Polytechnic University. This is my third year working as a full-time instructor. I have a lot of interest in mathematical modeling. I've been in charge of our school's efforts for math modeling competitions for a while, and that was a big part of what I did as an undergraduate and as a grad student. And I'm here today to tell you about some changes that we've implemented over the past few years to our calculus sequence starting last fall. So the reason why we've been thinking about calculus reform for a while now is because a lot of our students, particularly the ones who start with us in the fall, tend to really struggle in getting through the calculus sequence. A lot of them are here fresh out of high school and they're not really used to thinking about college level mathematics, which is typically much more focused on concepts and problem solving than just memorizing formulas, which is pretty big part of what high schools tend to focus on. So over the past few years, we've gradually been making some edits to our calculus sequence to try to help students along in this regard. Oh, I'm sorry. I think someone is raising their hand.
Sorry, I just wanted to ask you guys. I'd heard some years ago that Florida had made some changes similar to what we've done here in California, in that basically graduating from high school in Florida means ready for college level math. Do you guys have like a prerequisite for, you have Calc 1 prerequisite for Calc 2, right? But what about for Calc 1?
I'm not sure what it would be for Calc 1. A lot of our Calculus 2 students, the ones that actually started in that in the fall, come in with AP credits.
Okay, thanks.
So over the past few years, we've been making a few incremental changes to our calculus sequence. Most of them have been fairly simple things, just consisting of cutting some topics so that we can spend more time going over fewer things. But our most significant changes that we made in a while started last fall. I suggested that we try to take a much more applications focus to Calculus 2, and in particular to make differential equations modeling a much more prominent part of the class. And that's what I'm here today to tell you about. So my goals for today are to tell you a little bit about why I think making models based differential equations coverage a big part of Calculus 2, why I think that's a good idea. I'll tell you a little bit about how exactly we've been implementing it since last fall. And even though it's a little bit early, I can tell you a little bit about what we've seen as a result of that since then. So first of all, the main motivation. I personally feel like Calculus 2 is a uniquely poor way to introduce students to college level math. For a few different reasons. I have three main reasons, which I'll expand on a little bit. First of all, Calculus 2 usually begins with a review of Calculus 1 topics, things like basic anti-differentiation rules and the definition of what a definite integral is. And then the first few applications that you typically talk about after that are things like areas and net changes, which students will be used to from the end of Calculus 1. And both of those things immediately communicate to the student that Calculus 2 is going to mostly be a class about remembering formulas and techniques. And at least at the beginning, I guess maybe it can be, but that kind of mindset tends to really hurt students later on when you get to the more conceptually complicated topics like differential equations and Taylor series that really do require a deeper level of understanding. And it's also just not very representative of the kind of work that real STEM professionals actually do. Very little of it is really based on memorizing formulas and computing things by hand. It's more about understanding the ideas and being able to apply them to new situations. Second of all, and the thing that I find most personally offensive about typical Calculus 2 coverage is that the beginning of it is exceptionally boring. The first few topics that you typically cover are geometric topics like areas and volumes, things that no student cares about, and things that every student can definitely see are just made up applications that no engineer would actually put into practice. And that's a pretty terrible way to introduce them to college level math. My third main issue with typical Calculus 2 coverage is that it is typically presented in kind of an unintentional order. By its nature, Calculus 2 kind of consists of a grab bag of assorted things that continue on from Calculus 1 in various ways, but there's not really a whole lot of reason behind the order in which it's typically presented. The topics could honestly be presented in just about any order without really changing anything. And unlike Calculus 1, there isn't really any overarching structure or sense of progression throughout the course, which makes it a little bit unclear where everything is going and why we bother to cover it. So in order to try to mitigate some of these issues, we decided last fall to try making some structural changes to our Calculus 2 course. And the main thing that we wanted to focus on as a unifying design theme is what I would refer to as applications first. And what I mean by that is that the course is divided into a few different units. We begin every unit by talking about the end goals and the actual applications and the real world problems that we want to be able to solve by the end of the unit. And then we consistently refer to those goals whenever we're developing new theory or techniques within the unit to try to give students an idea of why we're covering things and what it's all leading towards. So the centerpiece of this approach, and something that we particularly chose to focus on, was the coverage of differential equations. Instead of covering it in the middle of the class, which is where it would usually go, we decided to begin with it because we thought it would be something interesting and different and highly motivating to give the students early on. And I think there are a few advantages to starting with differential equations in particular. So first of all, I think it's a much more interesting application than most of the other things you would typically cover in Calculus 2, and certainly much more so than things like net changes and areas and volumes. Differential equations give you a great excuse to talk about a lot of interesting and important real-world models that are actually convincing in a way that some of the other applications aren't. And it gives you a chance to look at some really interesting dynamics. This image that I'm showing right now is a particle physics simulation, which is based on differential equations. And that's a very typical thing to use differential equations for, because if you know physical laws, you know force. And if you know force and mass, you know acceleration. That's a differential equation, and that's a very natural thing to use differential equations to model. Second of all, starting with differential equations also immediately shows the students something very different than they're likely to have covered in high school level math, which hopefully serves as a faster way of showing them and not just telling them that this class is going to be different than what they're used to from high school, and it's going to require a different approach. And the last thing that I'll mention is, frankly, there's no reason not to cover differential equations early in the class. There's no reason it needs to be in the middle of the class. It's possible to define differential equations models and to do simple things like qualitative analysis without really needing that much calculus background. All you really need to know is that a derivative represents a rate of change, and there are a lot of useful conclusions that you can reach just by looking at when a rate of change is positive or negative or zero. You could introduce differential equations in Calculus 1, so covering it early in Calculus 2 is doable, and it also gives you an opportunity to review some Calculus 1 topics in more of an organic way, where everything is actually being applied to this broader topic of analyzing the behavior of differential equations models. So next, I'd like to tell you a little bit about what this first unit of our course actually ended up looking like last fall and also this spring semester. So I mentioned that the main design goal was to try to make everything applications first. And these are the specific end goals that we gave to our students at the beginning of the unit. There's two of them. Broadly speaking, one of them is about being able to take a differential equations model and to reach useful conclusions about it. That might come from solving the differential equation. You might be able to do that exactly for very simple ones, and if not, you have numerical solutions from Euler's method. And it also includes things like qualitative analysis techniques, like using slope fields and phase lines and equilibrium analysis. The second major goal we wanted students to actually get a taste of the modeling process itself and to be able to relate back and forth between a mathematical description of a real world problem. And that could go in both directions. We could give the students a description of a real world system and then ask them to come up with a reasonable way to model it using a differential equation. Or going in the opposite direction. If we give them a differential equation, we would like for them to be able to interpret why it looks the way it does and what each term actually means. We very intentionally wanted to design this unit to avoid just reviewing Calculus 1 material at the beginning of the class. So for fully the first 2 weeks of class, we did not explicitly mention anything from Calculus 1. Everything was related to developing and analyzing differential equations because we really wanted students to avoid immediately getting into this memorization-based mindset. So for the first week, for the most part, we just showed them some important prototypical differential equations. We showed them how you develop them, a little bit of how you analyze them and what their solutions look like, mostly simple classical models, things like exponential growth and spring mass systems. And the main goal for the full first week was simply to give students an idea of what differential equations are and what you use them for, and to try to convince them that they're an important topic that is well worth understanding in STEM applications. During the first couple of weeks, the main goal was to cover a variety of fundamental topics in differential equations, things like basic definitions, like defining what a solution of a differential equation is. And a bonus of that is that it allows you to review some Calculus 1 skills without explicitly telling the students that's what it is, because checking whether something is a solution to a differential equation, that's practice for differentiation. And there are certain very simple differential equations that you can solve just by using integration rules. And then we also covered a few basic analysis techniques like using slope fields and equilibrium analysis. And by the end of the second week, the students knew of a variety of ways to figure out the behavior of a simple differential equation. Week 3 is when we actually started to review some material from Calculus 1 by talking a little bit more about integral calculus and Riemann sums and net changes in the fundamental theorem of calculus. But it wasn't just presented as review for review's sake. This was all presented as necessary tools for analyzing differential equations, because solving a differential equation is very closely related to what you would use the net change theorem for. In both cases, you have information about a rate of change, and you'd like to figure out information about a net change. That's what you're doing when you integrate or when you solve a differential equation. Last fall, our coverage ended up being a little bit different for scheduling reasons. Last fall, we had a couple of major group projects for the students to work on that involved them taking differential equations models and doing a few things with them, like running an equilibrium analysis and solving them numerically. This spring, we made much more of an effort to try to incorporate group work into the class and to actually set aside class time for students to work on projects in groups. The main reason for that is because we think it's especially important for students to talk about new ideas with each other. Differential equations are sufficiently advanced that they're not the kind of thing that you can understand fully by just watching the instructor go through examples on the board. They're the kind of thing where you need to talk about these ideas out loud with your peers, and we wanted to give our students a chance to do that with group work. So the fourth and final week of our differential equations unit this semester consisted of a comprehensive group project to try to tie together a lot of what we had previously discussed. So we had them develop and analyze a population model that included a predation term. We had them apply equilibrium analysis to make a few conclusions about its long-term behavior. And then we had them solve the system under a couple of different sets of parameters using Euler's method. And that was followed by the first unit exam. That's just the first unit of the course, but we tried to make similar efforts to organize the rest of the course into these kinds of cohesive units that all have their own end goals and senses of progression. At the end of the course, we are planning to have a single week-long comprehensive project that will tie together lots of things that we've discussed throughout the various units, but with a particular focus on differential equations models and the things related to that we'll be seeing later in the course. So lastly, I'd like to talk about at least a few preliminary results. Just as a reminder, we've only been implementing these changes since last fall, so I don't really have very much official that I can say about the exact effects of all of these changes, and it's a little bit too early to make any strong conclusions. I will say that strictly in terms of numbers and scores, performance last fall and this spring seems to be pretty similar to what it typically is. That's been the case for all of the reform efforts we've made over the past few years. Student performance seems to be fairly insensitive to the specific ways that we changed the course. Spring performance is always much better than fall performance. I think there are a few reasons for that. Part of it is just because all of the students in spring are guaranteed to have at least some college experience, whereas the fall students are mostly new and mostly here from high school. Also, spring takes place sooner after fall semester than fall does after spring semester, so they've had less chance to forget material from Calculus 1. I think also a lot of our fall students are here from AP Calculus, which very much has a focus on memorizing particular methods for solving particular problems. And that's a very unhelpful mindset for the students to be in when we get to things like differential equations. So the students who have actually had Calculus 1 here with us are also a little bit better prepared for these stylistic changes. Unlike last semester, we actually do have a chance to see how some of last fall's Calculus 2 students are doing downstream in the classes that follow from it. I've heard from some of our differential equations instructors that this semester students, the ones who had our revised version of Calculus 2 last semester, they seem to be doing a better job of picking up some of the qualitative analysis techniques like phase line analysis and understanding what equilibrium solutions are and why finding them can be useful. So that's an encouraging sign. I can say definitely with confidence that reorganizing Calculus 2 in this way is definitely not worse than the usual organization of Calculus 2. And I see no reason not to present things in this way. The instructors like it more, and that's important. It's important to enjoy the way that you teach things. And I think that there are enough potential benefits for the students that it's a system that's worth continuing with. As for how the students themselves feel about these changes, that varies a lot from student to student. I've been told by some of them that they definitely appreciate the effort to actually tie class material to real-world applications. A lot of them are used to math classes being very pure and abstract and divorced from real-world applications, and they appreciate that we're at least making an effort to show them real things. There are a lot of students who seem to be responding to it more negatively, though. What they're used to from high school is that math is just memorizing formulas and computing things by hand. That's what they know, and it's what they're good at, and they regard anything beyond that as being hard, and they don't like it. Their response to the group work also varies quite a lot from student to student. There's definitely a long adjustment period getting the students used to a format other than just sitting through a lecture. Some of the students seem to really like it, and we've actually had a lot of groups getting together to study or to work on homework even without us prompting them to. That's not the case for every student, but I think it's important to try to use a variety of modalities. Some people respond very well to lecture, some of them don't, and I think having a class be taught entirely through lecture wouldn't be ideal either. As for changes that I'd like to see us make in future semesters, It is still the case that I wish we had more time to look at more different and more interesting differential equations models near the beginning, of course. There is a lot of official business for us to get through in terms of important definitions and important techniques. And I think that kind of goes against one of our main design goals, which was to get students immediately interested in the material and to not just regard it as being a list of methods to memorize. It's also been the case that in exams so far, the area where students consistently perform the poorest are questions where we just simply ask them to explain in plain English what part of a model means, why it's built the way it is, what a term in a model might mean. It is in general this idea of being able to translate back and forth between a real world system and the mathematical model that you would use for it. So I think that's something that we definitely need to give them more practice with and to focus on more. In conclusion, I don't want to overstate anything that we've done because essentially it just amounts to presenting the usual Calculus 2 material, but in a different order and with a more intentional focus. I think that there are a lot of potential benefits to this model, but there's also definitely a lot of refinements that could be made to it. So what I would really like to see is for more people to try adopting this kind of applications first approach, and in particular to focus more on differential equations modeling in Calculus 2. I know that there are many improvements that could be made over our methods, and I would love to hear what you're able to do with these methods. That's all I have for today, and thank you very much for attending. I have a question.
Yeah, I like this very much. I like many of the things that you said very much, and I like very much putting differential equations at the center of a Calculus 2 or even a Calculus 1 course. I had two thoughts as you were describing your course. One is traditionally a large part of Calculus 2 is infinite series, maybe power series. Do you connect that with the differential equations at all, or do you leave that out of your course?
I would like to, because there are definitely some deep connections, especially if you're doing things like actually looking at, say, the error in Euler's method. And by some descriptions, you can derive Euler's method using Taylor series. I think most of that is probably more advanced than I think what our students would be able to handle. It's something that I would like for us to touch on in the final project, because the main goal with that is to try to relate the different threads throughout the class as much as possible. So I definitely do want us to mention it. I'm not really sure how much we can really ask our students to do with it, though. I have another question.
Can you go to someone else? I have a contractor at the door. I'm sorry.
Oh, sure.
Oh. Adam, I can give you a comment if you wish. Sorry, I should probably turn on my cat. It's
yeah,
more
sure,
of a,
great.
sorry, turn on my, see if I can turn on my video as well too. So it's more, sorry, good morning, my name is Kerry. That was really great, Adam. Thank you very much for sharing. And I suppose it's just a comment. And for me, it is really great to see that focus of trying to change the mindset of students about what they regard maths to be and how they think about it. So to me, that was just, well, I'm in the process of developing a course at the moment, and it was really good to hear some of the things that you're doing, particularly with starting the same way. Start off with the maths application, start off with the thinking that you want. And it was really good just to hear what things were working for you and what weren't. So thank you very much. But
Well,
really that change of culture, that really, really excites me. So, and that how we sit there and how we actually get students to start thinking about mathematics other than just the set of equations and skills that we do. So that was great. Thank you.
Thank you very much. I'm definitely interested in hearing what you're working on. So please feel free to send me an email later if you like.
Okay, sounds good. I'm very interested if you want to follow up on any work around how we actually set up that change of mindset and what things we do to support. So yeah.
Yeah, that sounds great.
I just wanted to add that we finish our Calculus 2 course with 1 or 2 days on infinite series solutions to differential equations, which does nicely tie together those topics, those big topics in Calc 2. So I'd urge you to experiment with that a little.
Yes. Yeah, that is true. We use OpenStack's calculus, and that is one of the topics they discuss. So yeah, that would be a great idea.
Oh, hello. I don't know why I'm coming up as guest, but I thought I changed my. Anyway, that's neither here nor there. I'm probably the only high school teacher here, but I have taught differential equations. I started linear algebra for our county program, and
Oh, great.
so I very much like your approach, and I try to do this with my students. But I have a few questions. Are there, for your Calc 2 at your university, are there sections of Calc 2 that don't use this applications first process?
No, we have pretty strong coordination at this school. All of our different Calculus 2 sections teach from the same textbook. We all use the same exams and the same basic lecture notes. It's up to the individual instructor what exactly they want to present day to day, but everything is meant to be a united front.
I think that's a good approach. I was just curious because I was going to, if there was a difference, if there were different types of Calc 2, I was going to ask if there was attrition, right? If students were switching out of the applications first section and going to something they felt more comfortable with. That's not something that you can answer. The other thing, how deep into differential equations do you go with Calc 2 as far as types of equations and methods for solving?
Not very.
Okay.
Last fall, the only advanced solution technique that we talked about was separation of variables. That's a very natural follow-up to the substitution method.
Okay.
We didn't talk about any advanced solution techniques this spring. Only like first order systems that have explicit time dependence that you can solve just through integration. We really wanted students to focus on understanding the basic idea of differential equations and qualitative analysis, and not to get hung up on mechanical details of trying to solve them exactly. I would like to cover it if we could, but any of the students who actually need those techniques are going to see them in differential equations later anyway. So to try to make more time for the other material, we ended up having to cut that.
Okay, and then the last question is sort of a meta question. To what degree do you think the hand techniques that we traditionally teach in differential equations facilitate maybe student understanding of the concept? I think at some level it's tedium, and maybe they don't think about it, but at the same time, when they have to do the hand techniques, they're forced to slow down a little bit and maybe think about the parts. But I don't really have a firm opinion, so I was curious what your experience might say to a question like that.
I definitely agree. I think showing the various hand techniques a couple times is useful. I think a lot of classes tend to focus on them more than is really valuable, because after a while, students stop really thinking about what they're doing and just remembering it as a sequence of steps. Some hand techniques are more informative than others, like the kinds of techniques you use for like second order linear systems by like looking at particular solutions and homogeneous solutions. That's actually, I think, pretty informative, and it tells you a lot about what's actually going on. Other things like separation of variables, those are just algebraic tricks so that you can get something you can integrate. I don't think you really learn very much from that one.
And do the students, and I don't really have a good answer for this. Do they
Sorry,
ever
hey
have,
guys, sorry
Oh,
to cut you off. There's a session starting in 1 minute, so I'd have to like end the meeting and like join that one. Maybe you could like follow up with Adam. Adam, if you just like maybe like put your email in there or something, so like you could follow up with him.
Oh, sure.
I could do
Yeah,
that.
my contact info should be on my profile on the conference page. And if not, here's the title slide again.
thank you.
All right, thank you
Please
so
feel free
much,
to contact
everybody.
me anytime. And thank you very much for being here.
All right, thank you, everybody. Bye.